We have already learned how the net force, mass, and acceleration are related. Let's take another look at this relationship that is called Newton's second law of motion.
If the force is constant, then as the mass increases, the acceleration decreases. That means when applied the same force, the larger mass will have a lower acceleration. We also found that if the mass is constant, then as the force increases, the acceleration increases. In other words, on the same mass, a larger force will result in a higher acceleration.
Now, we're going to create a math formula to relate these three quantities. Let's start with the force and acceleration. We know that if the force gets bigger, the acceleration gets bigger. We also know if the mass gets bigger, the acceleration gets smaller. So we could include mass in the equation like this. A equals F minus m. But this won't work for two reasons. First, if the mass is bigger than the force, then the acceleration will be a negative number. Like if this was 10 and this was 20, the acceleration would be negative 10. That means the object would decelerate. We never observed that in the simulation that we used. The object always accelerated. The second reason this won't work is because the unit for acceleration is meters per second squared, and the unit in this formula, force, is in newtons, kilograms is mass. Now newtons is equal to a kilogram times meters per second squared minus kilograms. This right here is definitely not the same as this right here. The units don't match, so this can't work. Instead, let's try division. If we put the mass as the denominator, then as the mass gets bigger, the acceleration gets smaller. And this matches what we observed in the simulation. The acceleration won't be negative unless the force is negative. So that all works. Even the unit works. Acceleration is meters per second squared, force is newtons, and mass is kilograms, but a newton is actually equal to kilograms times meters per second squared, and the kilograms cancel out, leaving the unit meters per second squared, and that matches. So everything matches, so we have our formula. Nice job. Now remember, Newton's second law is abbreviated as force equals mass times acceleration. And remember, a strong force acting on a small mass will produce a really high acceleration.
Now let's try some practice problems.
What force is needed to accelerate a 20 kilogram mass at 6 meters per second squared? To figure this out, we first write our formula. F equals mass times acceleration. Now the next thing we can do is plug in our values. The mass is 20 kilograms, the acceleration is 6 meters per second squared. 20 times 6 is 120 newtons. It takes 120 newtons to accelerate a 20 kilogram mass at 6 meters per second squared. Now what force is needed to accelerate a 20 kilogram mass at only 3 meters per second squared? To figure this out, we once again write our formula. F equals m times a. Now we plug in our mass, which is still 20, but now the acceleration is only 3 meters per second squared. 20 times 3 is 60 newtons. Now that makes sense because a smaller force is needed to accelerate a mass at a lower rate. Let's try another problem. What will be the acceleration of a 10 kilogram mass when a force of 80 newtons is applied to it? Now we can't use the F equals ma the way it stands. We have to rearrange it with some algebra and get the formula A equals F over m. Now we plug our numbers in. The force is 80 newtons, the mass is 10 kilograms, which means the acceleration is 8 meters per second squared. Now, what would happen to the acceleration of the object if we doubled the net force acting on it? Now, we use the same formula, A equals F over m. But now we're plugging in 160 as our force and 10 kilograms as the mass, giving us an acceleration of 16 meters per second squared. Now you can see when the force is doubled, the acceleration was doubled from 8 to 16 meters per second squared. Let's try one more set of problems. What is the mass of an object that has an acceleration of 4 meters per second squared when a force of 24 newtons is applied to it? Well, we're going to take our formula, mass equals force over acceleration. And we're going to start plugging our numbers in. The force is 24 newtons, and the acceleration is 4 meters per second squared. So the mass of this object must be 6 kilograms. Here's another. What is the mass of an object that has an acceleration of 8 meters per second squared when a force of 24 newtons is applied to it? Same formula. Now we plug in our force and our acceleration, and we have a mass of 3 kilograms.
Now this makes sense when compared to the previous problem,
where the force of 24 newtons resulted in acceleration of 4 meters per second squared. A smaller mass would have a larger acceleration when applied the same 24 Newton force. Just remember, the force is the net force acting on the object. So let's try one more set of problems. What will be the acceleration of a 4 kilogram mass when an applied force of 50 newtons is acting to the right and a frictional force of 10 newtons is acting to the left? Now we'll have to use our equation, A equals F over m. Now we're going to plug in our values. Now the mass, we can see, is 4 kilograms. The force is 50 newtons to the right, 10 to the left, gives us a net force of 40 newtons. 40 over 4 is an acceleration of 10 meters per second squared. What will be the acceleration of a 2 kilogram mass when an applied force of 100 newtons is acting to the left and a frictional force of 20 newtons is acting to the right? Now once again, we'll use our formula, A equals F over m. We'll plug in our mass again, that's the easy one. We do have to figure out the net force. 100 minus 20 is 80. So this object will have an acceleration of 40 meters per second squared. Now that makes sense. It's a smaller mass being applied a bigger net force. That means acceleration will be a lot bigger.
So once again, when applied the same force, a larger mass will have a lower acceleration, and a smaller mass will have a higher acceleration. And if two objects that are the same mass are both applied forces, the one that has the larger force applied to it will have the higher acceleration.